Hey everyone, welcome back to quantprof. Today we are going to solve a Worldquant interview question. Check the description for more quant interview resources. Let's look at the problem. 16 ships are arranged in a 4x4 grid as shown. Our goal is to destroy all the ships. To accomplish this, we can drop bombs on specific squares of the grid. Each bomb destroys all the remaining ships in the row and column where it lands. For example, if a bomb is dropped on the top left corner of the grid, every ship in the first row and first column will be destroyed. Similarly, if a bomb was dropped on this square, these ships would be destroyed. So, if 4 bombs are dropped randomly on the squares of the 4x4 grid, with the possibility of multiple bombs landing on the same square, what is the probability that all ships are destroyed? Pause the video here if you want to give it a try. Here's the solution. Let A represent the event in which one bomb hits each of the 4 rows. For example, if the bombs land on the blue squares, every row will have at least one bomb, and hence, each of the 4 rows will be hit. Note that if one bomb hits each of the 4 rows, all ships will be destroyed. Similarly, let B represent the event in which one bomb hits each of the 4 columns. For example, in this case, each of the 4 columns will be hit. Again, if one bomb hits each of the 4 columns, all ships will be destroyed. We need to determine the number of configurations that satisfy at least one of these events. In other words, we want to find the number of elements in the set A union B. Applying the principle of inclusion and exclusion, we can express it using the following expression. Alright, let's find the number of configurations that satisfy the event A. The first bomb can be dropped on any of the 16 squares in the grid, resulting in 16 possibilities. Suppose the first bomb was dropped on this square. Since we need to cover all the rows, the remaining bombs cannot be placed in the same row as a previously dropped bomb. Therefore, the second bomb has 12 possible squares. Suppose the second bomb was dropped on this square. Now, the third bomb will have only 8 possible squares. Similarly, the last bomb will have 4 possible squares. Using the multiplication rule, the number of configurations that satisfy the event A is 6,144. Similarly, the number of configurations that satisfy the event B is also 6,144. Alright, let's focus on the last term, A intersection B, which represents the number of ways to simultaneously cover all 4 rows and columns. Again, the first bomb can be dropped on any of the 16 squares in the grid. Suppose the bomb was dropped on this square. The next bomb cannot be placed on the same row or the same column. So for the second bomb, we have 9 possible squares. Suppose the second bomb is dropped on this square. The third bomb cannot share a row or column with the previous 2 bombs, leaving it with 4 possible squares. Similarly, once the third bomb is dropped on one of the remaining squares, the fourth bomb will have only 1 possible square left. By multiplying these values, we obtain a total of 576 possible arrangements for this case. Now, by applying the principle of inclusion and exclusion, we find that 11,712 configurations satisfy at least one of the events. The total number of possible configurations is 16 raised to the power of 4, as each bomb can be dropped on any of the 16 squares. So the probability that all ships are destroyed is approximately 0.1787. Let's consider another problem. We have a fair 10-sided die with faces numbered from 1 to 10. What is the expected number of rolls needed until the least common multiple of all the numbers rolled so far exceeds 2,000? Try to solve it on your own. Hope you liked the video. If you want to learn how to solve these kinds of interview problems, we invite you to check out our course Quant Interview Masterclass, where we teach you how to think when solving difficult problems. We also cover the entire theory specifically tailored for quant interviews, along with over 1,000 problems. Thanks for watching, and see you next time. Until then, Godspeed.